Hello. Thank you guys for being here and thank you guys for watching. My name is Antoine and I am a rising senior at Mano Afterton High School in the Bay Area.
I'm Caleb, also from the Bay, and I'm a rising senior at Amador Valley High School.
I'm Nate, also from the Bay Area and also a rising senior.
Okay, so in our presentation today, we're going to talk about measurements at the nanoscale. There is plenty of room at the bottom. These are the words of Caltech professor Ryan Fearman in his presentation in 1959 about a study in about an invitation to enter a new field of physics. What Fearman was referencing to is the ability to move things atom by atoms. But let's first define the nanoscale. The nanoscale is when we measure things from 1 nanometer, when we use nanotechnologies or nanosciences from 1 nanometer to 100 nanometers. A nanometer is a billionth of a meter, or as Ben said, 1 times 10 to the negative 9th meter. As a reference, the width of a sheet of paper is 100,000 nanometers. So you might ask this question, why go so small? And there's a very simple answer. Because nanotechnologies have very different physical properties. For instance, they have a higher surface area than their bulk partners. They're also firm. We can make them move thermally using thermal solutions, and this is called Brownian motion. And this is very different than also the bulk materials. And they also can interact with biological molecules because they match them in size. That means that overall nanosciences open a completely new field of interactions with cells, and with cells at a smaller scale.
So this experiment was kind of explained earlier, but to recap, it was the experiment where we took olive oil and then diluted it with ethanol and then put that in a bucket of water to see the phenomenon where it forms a monolayer. So basically, olive oil is made up of fats, which are amphiphilic, which means they have a hydrophobic head because it's repelled from water, and a hydrophilic tail because it's attracted to water. And this is due to the polarity of the water molecules and the tail. So they attract, and the head is repelled by it because it's nonpolar. And so this forms a monolayer where all tails are touching the water and all the heads are repelled from it. So basically it's a uniform layer where all the heads are upright and all the tails are touching the water, similar to this analogy here. So basically demonstrated here, the people or the olive oil molecules are dropped from a plane or a dropper, and they're all in random configurations, but when they hit the ground or the water, they automatically go into this uniform structure where they're all upright, and it basically, the soldiers saying that they've been trained to be uniform, and this is because of the charges and their interaction with water.
Okay, so to build onto that, this concept with the monolayer, which is represented by the organized line of soldiers, can also be seen in the membranes of our cells. Except in that scenario, there are two layers, and they're kind of opposite facing, with the heads on the outsides and the tails on the insides. And this double layer is kind of used to let certain molecules and nutrients into the cell and out of the cell, and that's just one of the main applications of it. Another concept that this cartoon didn't exactly touch on from this experiment is the concept of using indirect measurement to measure data at the nanoscale. So for the experiment, what we did was we first measured the volume of the olive oil ethanol solution, which was done by first measuring that of one drop and then eventually finding of the whole solution. And then we watched, as explained by the other group, as it expanded through the baking soda, we measured the radius of the circle that the olive oil puddle was creating, and we used that to calculate the area. So with these two pieces of information, with the volume of the solution and the surface area, and also with the knowledge that it would sort of form like a layer that's sort of like a cylinder, our goal was to essentially find the height of the layer, which is only one molecule of oleic acid thick. So it's extremely small. And we were able to do this through the process of indirect measurement, where once we got both of the data points of volume and area, we were simply able to plug it into the formula volume equals area times height, and we were able to find the height. And this is essential because we can't simply get a ruler and measure something that's that small. It's only a couple of nanometers, which is like a billionth of a meter. 1 nanometer is a billionth of a meter. So it's amazing that we were able to use other measurements that are much easier to measure, such as volume and area, to find the height of the layer. Thank you guys for listening.
Let's say that I know that I've now formed a monolayer on some type of a substrate. Is there any way I could visualize that monolayer or the individual molecules or nanoparticles on that surface while also measuring the surface's topography?
So yeah, absolutely. So there was this experiment. I think it was done by George Washington. I'm not exactly sure.
Benjamin Franklin.
Oh, Benjamin Franklin. I confuse them all the time. Anyways, so so he had at the tip of his cane, he had olive oil, and he would pour it onto a lake. And what we saw is that since there was this monolayer, the surface was completely calm for the circle of the olive oil being dropped. And the rest was wavy. The rest of the lake with actual water was wavy. And that was the way to distinguish where there was the olive monolayer, because it was completely flat and the rest was wavy. That was a way to figure it out.
What if I wanted to image, say, just 2 or 3 molecules or nanoparticles on a surface? Is there any technique I could implement to do so?
Well, I assume you could use an electron microscope, because electrons have really tiny wavelengths. So when they hit the monolayer, it's the interactions that come out of that can be imaged, and because they're hitting the monolayer is really thin, and it's only 1 molecule thick, but the electrons are extremely tiny, so they're able to interact with it and then produce an image.
So I guess I'll add on to the question. So electron microscopes will give you a view of the surface, but it's not that good at measuring height, like topography. So it might give you sort of an idea if the surface is rough or not, but it can't really measure so much. But there was a technique that you saw, if you remember, on Monday afternoon when you went touring in the different labs. Do you remember what that was? Was
that the microscope that instead of using light or electrons, it used the probe that's only one atom thick at the very tip of it, mm-hmm. So it's able to run over it like a person reading Braille, mm-hmm. And so when it runs over it with that probe, it's able to feel the bumps, and therefore create an image that's really fine. And you can also code it to sense magnetism or charge, which could be helpful because the heads are nonpolar and the tails are.
That's true. Do you remember so everyone knows, do you remember what the technique was called? It's okay if you don't, but you said the words already. You just have to put them together. So you said scanning.
Scanning.
And the thing that's scanning it. Yeah.
Microscope.
Yeah. Nice. Good job. Any other questions from the audience? And if not, then let's thank our speakers.
Okay.